Let's continue now our discussion, and we are now in this three-phase system topic. Now, for a three-phase system, it is a system with three alternating voltages supplied to a load. So we have here in the figure, we have a waveform, a voltage waveform produced from A, and then another voltage waveform produced from B, and another waveform produced from C. So we can see here that the voltages are equal in magnitude, right? So the magnitude is equal, and also in frequency. So that means that the waveform, this waveform produced from A, has the same peak value as the ones produced from B and from C. And also they have the same frequency. So that means the intervals from this point to that point, they're just the same. Okay, but the instantaneous voltages, they're not equal. So what that means is that if you try to draw a line, for example, and when we say instantaneous, we are referring to at an instant or at a point in time. So what's the voltage from A, what's the voltage from B, and what's the voltage from C? Okay, so we can see here that the voltage at A is this value, but the voltage produced from the B waveform is right here, and then from the C waveform is right here. So at that instant of time, they don't have the same voltages. Okay, but the magnitude, that's the peak values and other voltages terms, they're just the same, and also the frequency. There are two types of three-phase systems, and we have this Y connection and the delta connection. We have already discussed this, and the Y connection, basically it has a Y shape, I mean in terms of when we compute it or when we represent it. But of course, in practical situations, that would be that this line or this phase, for example, this phase A, and then the phase B and phase C, they are connected to a neutral line. Okay, so right here, you can see this subscript or letters A, B, C, and that refers to the phase voltages. V phase, so that refers to phase voltage. Okay, so we have phase voltage A, we have also phase voltage B, and we have also phase voltage C. And right here, from A to B, we can actually have another source or have another voltage term, and that's what we call the line-to-line voltage. So from line A to line B, so that's the line-to-line voltage. We can obtain another voltage source, and right here from line B and C, we can also get another voltage source, and from line A to line C, we can have another voltage source. Okay, so for this connection, Y connection, it's typically or the characteristics of this Y connection is that it has a high voltage, and that refers to the line voltage, but the current is low. For a delta connection, we have this typical shape, and again, in practice, it wouldn't be that geometry or that shape, but the practical connection is that all these phases, let's say the phase A and phase C, they're connected here, they're connected together, and A and B, they're connected together, and B and C, they're connected together. So just the same with our Y connection, this A right here, A, B, and C, they are referred to as the phase voltage. And this one from from line A to line B, we can obtain a voltage source, which is called the line voltage. So that's the line voltage from line A to B, and we can also obtain another voltage source from B to C or from A to C. And this delta connection is characterized as the low voltage, high current. And now for the computations regarding the relationship between the phase voltage and the line voltage, or the line current or phase currents, we have here as shown in the table. So for Y connection, the phase voltage is equal to the line voltage divided by square root of 3. And this square root of 3 is, if you take the value of the square root of 3, that's around 1.73. Right, so 1.73. So that's why we have said earlier that the line voltage for Y connection is greater than the phase, or it has this high voltage, low current. Okay, because that's 1.73 times greater. Okay, but for the current, it just says that the phase current is equal to the line current. And for the delta connection, it's the other way around, that the phase voltage is equal to the line voltage, but the current is equal to I sub L divided by square root of 3. So high current, and we're referring to this line current. But for the apparent power, we have these equations. Recall that this apparent power, the symbol that we use is S, and this one for the true power, this is we use the symbol P. So here for the apparent powers is simply square root of 3 times the line voltage times the line current. So because of these three-phase systems, we have this additional term, which is square root of 3. And again, as I've said, that this value square root of 3 is 1.73. So that's why the three-phase power is or has 73% more power than the single phase. Okay. And when solving for the true power, we just simply include this power factor. Okay, now let's go on to the review questions. Alright, number 157. A three-phase AC generator is blank in physical dimensions than a single-phase generator of the same rating. The answer here is that the three-phase AC generator is smaller in dimensions as compared to the single phase. The answer here is letter B. Okay, so if we try to also explain this in terms of analogy to internal combustion engines. So imagine that you have this single piston, or single cylinder piston, right? And compare these ones, and compare that to if you have some smaller cylinders, but of course that would also deliver the same power. Okay, so in terms of physical dimensions, for a single phase, this is larger as compared to this ones. Okay, number 158. The power of a three-phase system is larger in what color as compared to single phase? This is 73%. Letter B. Number 159. It refers to any electrical system that has more than one waveform present. So the answer here is letter D, polyphase. We're in three-phase and two-phase systems. They're a part of this polyphase. Number 160. In a three-phase system, the instantaneous voltages of the three voltages are not equal. Letter D. Number 161. In a three-phase system, the voltages are equal in both magnitude and frequency. Letter C. Number 162. In 162, in a Y connection system having a phase voltage of 440 volts and a phase current of 10 amperes, determine the line voltage and determine the line current. So we have here a Y connection, right? And we have here the phase. And recall that in our table we have this, that in terms of voltage and in terms of amperes, for a Y connection we have V phase is equal to the line voltage divided by square root of 3, and this one, the V phase, is equal to the line voltage. But here in terms of the current, here we have I phase is equal to I sub L all over square root of 3, and this one, I phase, is equal to I sub L. Okay, so the given is we have 440 each, right? Or let's write it here. We have V phase is equal to 440, and our phase current I phase is equal to 10 amperes. Okay, so therefore, since this is a Y connection, right, since this is a Y connection, then our line voltage is equal to V phase times square root of 3. So this is 762 volts. And this one for I sub L, this is the same as the phase voltage, which is 10 amperes. So therefore our answer for 162 is letter C, and for 163, this is letter A. Okay, next item. Number 164. Right, number 164. In a delta connection system having phase voltage of 220 volts and a phase current of 10 amperes, determine the line voltage and determine the line current. So let's write it here. Our phase voltage 220 volts and our phase current of 10 amperes, but our connection is delta connection. So therefore our phase voltage is just equal to our line voltage, so that is equal to 220 volts. And right here, for our line current, so line current is just simply square root of 3 times our phase current. Okay, so let's try to compute. So we have here an answer of 17.3. It's 17.3 amperes. For 164, the answer is letter C. That's 220 volts, and for 165, the answer is letter C. Okay, and then last problem, we have 166. A Y-connected system has a line voltage of, okay, so we have a Y-connected system and we have a line voltage, right? Line voltage of 440 volts, and our line current equal to 10 amperes. What is the total three-phase power if the power factor is 0.9? And what's the real power if the power factor is 0.95? So note that when we talk about apparent power, we don't consider the power factor. So therefore, our S is just simply square root of 3 times the line voltage times the line current. So if we substitute the value, what we get is this is 7.62 kilovolts ampere kVA. And for our real power, we have you can just use the 7.63 S times the power factor. So we have 7.24 kilowatts. So for 166, we have a value of letter C, and 167, the answer is letter B. Okay, now we'll go back to our lecture discussions, and we'll have a new topic on electric machines. Alright, this is our next topic for the review course in agricultural electrification and controls. And the title of this lecture topic is electric machines. For the contents, we'll first have a brief introduction regarding the electric machines, and then we'll get into the details of electric motors and electrical transformers. And there's still another one electric machines that we will not consider here, and that's the electric generators. Anyway, for the introductions, here are the common types or common examples of electrical machines. So we have the electric motor, we have the generators, and we have the transformers. Okay, so right here, for when we say electric motors, basically it's a machine that converts electrical energy. So you input electrical energy by plugging the, let's say, this wire on or in a convenience outlet or other I mean, that depends upon the size, of course. So it could be tapped to some source. Okay, so these electric motors, they're electrical machines that converts this electrical energy into mechanical energy. So as I've said, we have this electrical source as the input, and the output would be the rotation of the shaft. When we say generator, it's the other way around of the electric motors. So for a generator, you input a mechanical power by probably connecting this to an engine, for example, right? Engine or other means, and because of the engines, then it can, because the output of the engine is a rotating shaft, then if it is coupled to this shaft of this generator, then the output would be electrical or electrical energy. Okay, so that's what we call a generator. And for a transformer, it's an electrical machine that converts electrical energy. So the input is electrical energy, and the output should be, okay, this must be electrical energy. This must be letter M. Okay, so input electrical energy, the output is also an electrical energy. Okay, so again, for electric motor, the input is electrical energy, the output is mechanical. But for generators, the input is mechanical because of this rotating shaft, and the output would be electrical energy. And for transformers, the input is electrical, output is electrical. Now let's get into the details of electric motors. Electric motors are electrical devices that converts electrical energy into mechanical energy, and we often found this in driving processing equipments. Okay, so such as this one, and I'm thinking that this is a hammer mill equipment. Okay, so to drive this, okay, because we need a rotating shaft, and we need power and speed, and therefore we use this belt drive in order to vary some parameters, let's say speed and power also. Okay, so we have this hammer mill equipment, and the power source is an electric motor. Okay, another one is this electric motor that's used in a rice mill equipment. Okay, so this is the electric motor, and we have this driven equipment. Okay, and here another one is we use the electric motor to power the axial blower or fan for a reversible flatbed dryers. Right, so we have here, that's the reversible dryer, and the ones driving this rotation, or the ones providing the power for rotation, is an electric motor. Okay, so we have the shaft, output shaft rotating, and it's connected to the shaft of this blower through most likely this is through belt drives. Now, for the types of electric motors, generally motors are classified according to the type of power used, so that could be AC or DC power. Okay, and the motor principle of operations, and it uses magnetism and electric currents to operate. So we have here we have the types of electric motors, and it can be classified as AC motors or DC motors or universal motors. When we say AC motors, then of course the power source is AC, and in this type of motors you can further classify it like, for example, single phase AC motors or three-phase AC motors. And then right here we have this, it could be an induction type or synchronous or squirrel cage or wound motors. For a DC electric motors, then as the name implies, that's a type of electric motors that where the power source is a DC. And when we say universal, then it can just run on both AC and DC. Okay, so right here for an AC motor, this is typically characterized as fixed speed motors. Like for example, the RPM is 17, let's say 1780 RPM. But this one, you can vary this. You can vary the speed. Although, of course, if you provide controls, then like for example, the variable frequency inverter or variable frequency drives, then of course you can also vary the speed. Now for the motor constructions, we have these parts. This part is the ones that's rotating. That's what you call the rotor. And this one, the stationary part, the windings right here, that's what you call the stator. And we have of course, enclosures. And you also have fans at the end, right? And bearings and still many other parts. Okay, now for the types of rotor constructions, we have this squirrel cage and wire wound type. Okay, so the difference is that in this rotor designs, this one has windings, whereas this one it's not a winding, or it's not a wire wound. And right here we have we have different size of electric motors. We have 5.5, 7.5, but it shows the difference between this wound rotors and squirrel cage. Right here, if you would notice, we have a 7.5 kilowatts, and that's the size for a squirrel cage. But this one, this electric motor, this is just 5.5, yet the size is larger as compared to this one. Okay, so sometimes we also need to have some conversion, like for example, if there's a, say, a blower for the dryer. Okay, so or in the earlier picture that I've shown you, that the actual fan or actual blower is driven by an electric motor. Now what if we want to change, and instead of using an electric motor, we want to use an engine? Okay, so if we want to use an engine, then what's gonna be the size or the capacity of the engine? Okay, so we have these conversions, and this one also. So for HP motor, that's equal to 2/3 HP of engine. So 1 horsepower of motor is equal to 2/3 HP of engine. But for human power, we know, or we have learned in, let's say, agricultural power engineering or farm power sources, we have learned that human power can produce, I think that's 0.1. Okay. Anyway, I'm not sure about that. You can just check that out. That's 0.1 or something, 0.1 HP. So the conversion of human power to electric motor power is that 1/4 of horsepower of motor is equal to 1 HP for a man. Okay, now let's move on to this graph, and that's about motor currents. So when I switch on, let's say we have here an electric motor, right? And let's say we have some switches right here, that if I press the on button, okay, so if I press the on button, of course it will draw currents, okay, from the source. So at first it will produce a spike, something like that. Okay, so it will produce a spike, and then after some seconds it will go down, and then there's going to be something like a constant currents. So the first one, or the spike currents, that's what we call the inrush currents, and that's around, I think, 4 to 6 or 4 to 8 or 6 to 8 times of this running current. Okay, so right here we have the time, so you can see that that the moment you push the button, then there's going to be a spike, and then it will go down at some few seconds. It will go down to normal running conditions or normal running currents. Okay, and this current, this is what we call the running current. Okay, so we have here, I have included here the OL device and then the circuit breakers. OL device, overload relay. This is a protection device for this running current. And right here, this is another protection device for the circuit breaker. So therefore, how many current informations do we encounter here? We have, okay, number one, we have the inrush current, and this is this refers to this spike right here. That's the inrush current, and for the full load amperes, that's the running current, and for the nameplate current, that's the current that you can see in the nameplate of an electric motor. Okay, so in terms of switching, previously a knife switch is used, and it looks like this. So we have here, let's say, terminals and another terminals right here. That when we, okay, so let me draw the side view of this. So this is the knife switch, and when I press this down, right, there's going to be a contact. I mean, the circuit will be closed, and therefore um, it will provide power to the electric motor, and this electric motor will run. Okay, so previously knife switch is used, but because of many disadvantages, the use of contactors are rather used, because when when this, let's say, when this knife switch comes into contact, then there's there's a possibility. Okay, there's a spark. Okay, so if there's a spark, then of course the safety of the operator will also be affected. And also, as you open and close the circuit through this knife switch, then of course there's going to be a damage on the terminals because of that spark. So because of those disadvantages, then we now have the magnetic contactors to switch the electric motors. So a contactor are operated electromechanically without manual intervention. So let's say we only have these buttons connected, so we can have on or start, and we can have off or reset. So once I press the on and start, uh, I'm not exposing myself uh, to the electrical arcs compared to uh, this knife switch. In that way, this is more safe. Okay, so used for switching a current on and off in a circuit. Okay, now, based on the definition, this is a standard organization. It says that, or it describes contactors as devices to repeatedly establish and interrupt an electrical power circuit. Okay, now another one is that, what is this motor starter? Now, basically, motor starter is just a contactor plus overload relay. So this protection, the running amperes. So if we have this contactor plus the overload relay, then that's what we call the motor starter. You know, for the how do you connect the electric motor? So let's say we have this electric motor. This is in three phase, and we have three terminals right here. Okay, so that terminal can be found right here. Okay, so that a terminal is then connected to this overload device, right? And then after that overload device, it is connected to a circuit breaker. Sorry, a contactor. It's a contactor. Okay, overload relay, and then right here we have the circuit breaker and to the source. Okay, so at that configuration, then there's gonna be a rotation, and let's say we have a clockwise rotation. Now, if you want a reverse direction, then we can just simply uh, interchange this connection. Okay, so instead of having straight, then we'll just have to interchange these connections, and we can get a reverse direction. Okay, now let's go to the nameplates of electric motors, and I want to highlight another parameter here called the service factor. Service factor is the permissible amount of overload a motor can withstand while remaining within defined temperature limits. So right here, we can see that we have volts specified, and says here 230 volts, and the hertz, the frequency, that's 60, and the insulation class, and we also have this SF, that's our service factor, and it says here 1.15, and the description of service factor is this one: is the permissible amount of overload a motor can withstand while remaining within defined temperature limits. And right here we have also the number of poles. So for 4 poles, then what's the horsepower? It says here 3 horsepower, and what's the amps, and what's the speed in RPM. Now another one is we have this nameplate, and it says 3 HP, 230 volts, 13.5 amperes. Okay, and many other informations. Right here we also have, if you notice, this delta and this Y. So if you can see here that in this delta we have a voltage of 220 to 240, right? But for Y connection, that's 380 to 415 volts. Okay, so high voltage. But in terms of amperes, we have 1.3 to 1.2 amperes, and we have also ampere rating if we connect this electric motor in Y. Okay, so in other words, this electric motor can be connected either in delta or Y, depending upon your source voltage. And because of the source voltage, then of course you will have a changes in the in this amperes. Okay, and take note, this is in 50 hertz, but if you connect that in 60 hertz, then you have another range of voltage right here. Okay, so now let's go on to our review questions. (168). It is an electrical machine that converts the electrical energy into mechanical energy. This is electric motor. Number 169. It is an electrical machine that converts the mechanical energy into electrical energy. This is generator. Number 170. It is a process of reversing the polarity of the rotating armature. This is called commutation, and this is a term you would encounter in electric motors. This is letter B. Number 171 is a type of electric motor where the speed can be controlled smoothly down to 0. This is letter B. Number 172 is a type of electric motor where the speed is fixed, such as 900 RPM or 1800 RPM and so on. This is letter A. Number 173 is a type of electric motor where it can run on both AC and DC. Okay, so this should be, okay, the answer should be universal. Okay, universal motor. Okay, so let's just write letter. This is letter D. Okay, next item. 174. For a given power, a single phase motor is blank the 3-phase motor. The answer here is letter A. Number 175. If a motor is used in driving a corn sheller machine, it should be able to, letter A, drive the load at the proper speed, of course. Letter B, start the load, and this is also true. Letter C, withstand the abuses of its surroundings. So the answer here is letter D. number 176. A 6 HP engine used to drive the blower of a 6-ton flatbed dryer is to be replaced by an electric motor. What should be the size of the motor? So recall our equation that the 6 HP for engine, this is 2/3, right? Times 2/3 is equal to 1 HP, or HP of motor. Okay, so 6 times 2 divided by 3, this is 4. Okay, so this, since there's no 4 in the choices, so we have to round it up to 5. Okay, to 5 HP. Okay, next item, number 100. Okay, this is letter C. Number 177. If a small corn sheller that has been operated by hand is to be replaced by an electric motor, what is the minimum size of motor that can do the job? So this is just the conversion. So the answer here is letter A. Number 178, a universal motor means it can run on either AC or DC. This is letter A. Number 179, types of current information found in an electric motor. So we have inrush, we have nameplates, we have the full load amperes. The answer here is letter D. Number 180, in the nameplate of an electric motor, it is a multiplier that is applied to the motor's normal horsepower rating to indicate an increase in power output or overload capacity that the motor is capable of providing under certain conditions. This is service factor. In number 181, typically the inrush current of motor is 6 to 8 times. This is letter A. And number 182, the starting current of an electric motor is blank compared to its running current. So recall this graph. So we have a spike, and then we have this drop, and we have this constant running amperes. So the answer here is letter A. Number 183. Compute the input current in a 5 HP electric motor used to drive a hammer mill at 2,200 RPM. Input voltage is 220 volts and a power factor of 0.98. The working equation is just simply P is equal to VI, right, cosine theta. This is our power factor. So you have the 5 HP, right? In this, you have the 5 HP, and you have to convert that to watts, of course. This is in volts. This is in amperes, and you have this cosine theta, which is equal to 0.98. So you can solve for this current. The answer here is letter C. Number 184. When an electric motor is rated 10 HP and above, it is to be operated at what source? Okay, so this should be operated at or using 3-phase source, letter D. Number 185. A motor mounted in an axial fan for the blower of a flatbed dryer is operating at higher than normal temperature. So most likely, what is the possible cause, or what are the possible causes? For letter A, it says that it is overloaded, and for letter B, it says that there is a loose connection in the overload relay, and for letter C, the line frequency is incorrect, and letter D, it is a hot summertime. So the answer here is that if there's a loose connection in the overload relay, that's also probably possible, or it won't provide any power. Okay, so that's one answer. This is not the best answer. For letter C, the line frequency is correct, then that would, if the line frequency is correct, then of course you wouldn't be able to power the electric motor. And for letter D, then of course that's not also the answer. So the answer here is letter A. Again, I just would like to say about this letter B, if there's a loose connection, then probably it will not provide the power because of this loose connection. So the best answer here is letter A. Number 186, a three-phase motor was installed in a blower for body cleaner, but the rotation needs to be reversed. What should be done to correct the rotation? So here we have a situation that let's say we have a rotation, a clockwise rotation, but what we want is a counterclockwise rotation. So how do we do that? Now for letter A, it says that we are to remind the stator windings and recall that the stator is just, or it's a part or component of an electric motor. Inside the electric motor, where there's a lot of windings, and it says for letter A that you have to do some rewindings. And for letter B, install a forward reverse control circuit, which is also possible. And for letter C, reverse any two connection of motor leads, and this is what we have talked about. And letter D, install a frequency inverter device. And for letter D, if you install a frequency inverter device, you're just actually changing the speed, but you're not changing the rotation. For letter A, increase the voltage source, and of course, and that would damage the electric motor. If the motor is specified to run at 220, then you shouldn't increase the voltage source. So the answer here is the best answer is letter C. For 187, what electrical protection device is used to protect the running current of the motor? So that refers to this one. So the protection device is overload relay, and right here the protection device is circuit breaker. So the answer for number 187 is letter B. Okay, now we're done, and we'll move on to our next topic, and that's the topic about transformers. Okay, now for our next topic, we'll talk about transformers. And it says here that transformers are electrical devices consisting of two or more coils of wire used to transfer electrical energy by means of a changing magnetic field. So we have here a lot of different types of transformers that you can find in electronic devices and even in electric power distributions. And the principle of operation is that we have this coil, that's wrapped around this iron core. Okay, so we have a windings on this side, and we have another windings on the other side, on the load side. So here, this is our source, and right here we have our load. Okay, so that depending upon the number of windings, then there's an effect in the voltage and in the current. Okay, so let's say this is our this is what they call as the primary windings. Right here, this is our secondary, or this one right here. We have the secondary windings. Okay, so we can say that let's say we have this few number of windings at the source side, but here on the output side we have more windings. And what that means is that if you have more windings, then you have a high voltage on this output. Okay, and If this is high voltage, then this would be low voltage. So therefore, if you have this kind of transformer where you increases the voltage, okay, from the primary windings, or from this source side to the load side, then that's what you call as a step-up transformer. But if you have a transformer that decreases the value of the voltage, then that's what you call the step-down transformers. Okay, so note that this is in terms of voltage and amperes, and right here we have also voltage and amperes in these windings, but the energy, in terms of energy, they're just the same. And that's why we mentioned, or we discussed earlier, that the transformers, electrical transformers, they are electrical machines that converts electrical energy into electrical energy from this source to electrical energy, except that in terms of voltage and amperes, we have a different value. So for the working equations, we have this N sub P, which means the number of turns, right? Number of turns in the primary windings over the number of turns in the secondary windings is just equal to this one. That's the voltage, and voltage in the primary windings and the voltage in the secondary, which is equal to this ratio. This is the current. Okay, now we'll go on to our review questions. Alright, now for 168, it is an electrical machine used to transfer AC energy from one circuit to another. This is letter C. Number 169, it is an electrical machine composed of two electrically isolated coils and operates by electromagnetic induction. This is letter B. Number 170, this is a type of transformer with secondary voltage is greater than its primary voltage. So that's a step-up transformer, letter A. Number 171, it is a type of transformer that produces secondary voltage less than its primary voltage. This is called a step-down transformer. Number 172, a transformer has 400 turns on the primary. So let's write here, our primary has 100 turns and our secondary has 100 turns. And if the volts, if 120 volts are applied across the primary windings, so this is our voltage, it's 120 volts. Calculate the voltage induced in the secondary. So recall that in our relationship that the ratio of the primary windings, the secondary windings is equal to the voltage in the primary windings divided by the voltage in the secondary windings. Therefore, V sub S is just equal to, okay, so our V sub S is our primary voltage 120 volts times the number of turns, so that's 100, divided by the number of the turns in the primary side. So this is 400, so this one should be 400. So the answer here is Vs is equal to 30 volts. So number 100, sorry, this shouldn't 168. This must be 188. Okay, 188. And this one is 189. And this one is 190. This one is 190. 1. Okay, so for 192, this is our problem. 192 is letter C. And 193, for 193, a transformer has a 10:1 ratio. Okay, if, as it says here, that NP all over NS is equal to 10. Okay, and if the primary voltage is 120, determine the voltage on the secondary. Okay, so therefore 10 is equal to VP, the ratio of the primary voltage to the secondary voltage. This is just Vs is equal to 120 divided by 10, that's 12 volts. 193 is letter A. And for 194, transformer has a 8:1 ratio. If the primary has a current of 100 milliamperes, determine the current across the secondary. So you just have to apply the relationship, except that for the current, this is secondary all over primary. Okay, so the answer here is letter D. This is our fifth topic for the review course in agricultural electrification and controls. And in this topic, we'll talk about motor control devices. For the contents, we'll first discuss the standards from which these control devices are specified for, and then we'll have some brief discussions about the mechanical switches, control relays, signaling devices, and sensors. For the standards, we have here the list of some standards related to the electrical components from which these control devices are specified for. Okay, so first we have the ANSI, and that stands for the American National Standards Institutes, and then the next one is the DIN, which stands for this words right here, or if we translate that to English, it's the German Institute for Standardization. For the JIS, that's Japanese Industrial Standards, and this one, the NEMA, that's National Electrical Manufacturers Association. For the IEC, that's International Electrotechnical Commissions. And now for the overview of the control devices, these are just some, and the first one is the mechanical switches. So they are devices that's intended to make a closed circuit or open a circuit. And we also have control relays, which can be a switch or something like an electromagnetic switch. Okay, so that's the control relays. And we also have signaling devices, which indicates that, for example, we have a yellow light that turns on. Then what does it mean? Is the equipment in idle condition or fault condition or running conditions? Okay, so we'll talk about that. And we also have right here, this is actually this must be sensors, right? So sensors, control devices that senses the physical, let's say the physical environment, and convert that into electrical signals. Okay, so for the first one, we have the mechanical switches. Mechanical switches, they open or close the circuits, and there are a lot of mechanical switches. So we have, for example, push button switch or the drum switch or selector switch. Okay, so this one is a selector switch, wherein you can, if you rotate this knob, then you can switch some circuits on or off, for example. And we have also push button switch, and some switches, they also include indicator lights. Okay, and other switch, like for example this one, I think this is a limit switch, wherein if there's a mechanical action that pushes this one, so that could be um, that's actually can trigger, okay, to close or open the circuits. Okay, and we also have float switch and foot switch, which means that the switch is being operated by a foot. Okay, the next class is the control relays. Now, when we say control relays, basically it's just an electromagnetic switch, and it allows switching for high power circuit from a low power circuit, just like the conductor. Okay, so you are switching a high power circuit, but you're actually using electromagnetics. And the word solenoids, they are a specific type of electromagnet converting electrical energy into linear motion. So when you supply energy, electrical energy, then there's gonna be an action or a response of linear mechanical motion. Okay, also we have timers, which serves as a critical function in motor control by managing events. So for example, I have an electric motor. Okay, so instead of not having, let's say this is our on. Okay, so this is our on switch, and we have this off. Okay, so if I press this, if I press the on, right? If I press the on, then it will turn. This electric motor will turn immediately. But if I install a delay switch, it could be, it can be a delay like after, let's say, 3 seconds, or depending upon your setting here. So if I install or use a delay, then if I press this, then after 3 seconds, that's the time when it starts to rotate. Okay, so those are timers. Okay, another class is the signaling devices. Okay, so signaling devices, these are devices that provide a visual and or sound indication about the status of an industrial process. For example, if the green light turns on, then what does it mean? Or if the red light turns on, then what's the meaning, or what does it indicate? And if we have this yellow light, and then that depends upon the standards. Like for example, for the using ANSI standards, or using DIN standards or JIS standards, then it could have different meanings. When say red light, for example, probably here in ANSI that's default, that's fault, or here that's maybe idle, and then this one is running conditions, or the machine is in running condition, therefore you have to be alert, or something like that. Okay, that's the point here, that there's a lot of we need to understand also the standards, because for example the red light could mean different things for the different standards. Okay, next one is the sensors. Sensors, they convert the physical action to be measured into an electrical signal. For example, we have a thermostat, right? So if we have a thermostat, this is a device, a control device, that once it senses, like for example, if your thermostat setting is just 20 degrees C, okay, so once it reaches let's say once it reaches above this temperature, for example, you reaches 25 degrees C, then it will actuate, or it will send electrical signal to the, let's say, compressors, so that the refrigerant will cycle in the components, okay, for a refrigeration systems or air conditioning systems, or things like that. Okay, so the thermostat, that's the sensor, and when we say thermometer, That's a device that measures the temperature. Okay, so we can also have humidistat if we want the humidity to control, or to or the humidity is the physical action that we want. And this one is also a proximity sensor that when it senses, let's say, this distance, then it can trigger something, or it can turn on the electric motor or something. Okay, so now let's move on to our review questions. Okay, number 195. The meaning of NEMA, this is National Electrical Manufacturers Association. This is letter B. Number 196, the meaning of IEC, that is International Electrotechnical Commission, letter C. Number 197, the meaning of JIS, letter C. And number 198, this is letter C. Okay, number 199, they are control devices, whether operated by hand or some other object pressing it, and is used to stop, start, or redirect the electrical current passing through them. The answer is mechanical switches. Number 200. These are control devices consisting of coils of wire acting as electromagnets that pull a plunger into the core when energized. Okay, so these are control devices consisting of coils of wire acting as electromagnets that pull a plunger, and this, if there's a plunger, then this should be a linear action. Okay, so this is a solenoid, letter A. Number 201, they are type of control devices used to alert the operator to a pre-specified condition. So these are signaling devices, letter B. Number 202, it is a type of control devices designed to respond to a specific condition and pass along that information or response to a switch. This is letter D, sensors. Okay, moving on. 203. It is a type of switch commonly used for starting and stopping motors. Okay, so we have contactors, although it's a switch, but we still need switches, and the switches that we need are usually push button switches. Okay, so this is letter A. Okay, so recall that this, for example, this is our contactor, and we have here our overload relay. So there's no switching right here, right? There's no component wherein you can switch, turn on or turn off. There's just actually a something like a relay that you can control a higher power from a lower source. But of course, you still would need a circuit for controlling, for turning on and turning off. So this is something like an aid, or something like an assistance. So right here we need push button switches for on, for start and stop. So this is letter A. Number 204, it's a type of switch that operates in a manner similar to toggle switches, except that the operating mechanism is cam-like device. This is letter B. Number 205, it's a type of switch used when no physical contact should be made with the item detected. Okay, so when no physical contact should be made with the item detected, this is a proximity switch, because the float switch, it has a contact. The photoelectric switch, it has also no contact. I mean, it's just a switch actuated by the sunlight, or by light. Okay, so photoelectric switch. The answer here, the best answer would be between B and letter C. Okay. Now I guess the differentiating word is the item detected. So this one should be letter C because of the keyword item detected. Okay, number for the limit switch, it has contact, or it's a switch wherein it also has a contact points. Number 206. 206. Poultry housing owner would like his perimeter lighting be automatically off during daytime. What switch should be installed? This is photoelectric switch, letter B. Number 207. Which type of switch is suitable to be used for measuring the level of granular materials in a tank? Okay, so this one, level of granular materials in a tank, or should be, let's say, water, for example. This is our tank, and we have this, let's say, some switch that floats. Okay, so if we have this water, and at some portion it can turn off or turn on. For example, in this level, the pump is off, but then at this level it can also specify that pump to turn on. Okay, so that's one of the application of this float switch. But right here in our question it says granular materials, so I'm not sure though if it is also possible for granular materials, but the answer here is letter A. Number 208. It is a commonly used device to monitor a system, and in the event that pressure reaches a dangerous level, it opens a relief valve or shut the system down. Okay, so this is a pressure switch, letter A. Number 209. In order for water not to overflow in the water tank of a poultry farm, what would you recommend as an agricultural engineer? Letter A. Install a float switch to shut off and on the pump. Letter B. Install a motor controller to limit the pumping speed. Letter C. Close the valve manually. Letter D. Close the tank when it's full. Okay, so for letter B, if you install a motor controller speed, then probably it would affect your pumping capacity or your head capacity. So this is not an answer. For letter C, close the valve manually. That is also possible. Or the letter D, close the tank when it's full. Or if you have knowledge regarding the switches, then the best answer is letter A. Number 210. A mist sprinkler irrigation system is to be designed to provide the required head requirement for the pump system. As an agricultural engineer, what would you recommend to control the head requirement of the pump so it can deliver water to the emitters? Okay, and take note of this term head, which is actually related to pressure. So this is letter C. Okay, number 211. A device consisting of two unlike materials bonded together and expands with different rate when heated, providing physical signal and converts it to electrical signal. Okay, so they are similar metals. Let's say this is our metal number 1, and we have another metal that's being spliced. Right? And once it is heated, so let's say we have heat, it's being heated right here, then it can send an electrical signal. So this is called bimetallic sensor, letter B. Number 212. A sensor that changes internal pressure when temperature changes and uses a temperature sensitive liquid. I think the keyword right here is temperature sensitive liquid. This would be capillary tube sensor, letter C. Number 213, a cylindrical device with several deep folds that expand and contract in response to pressure, inside of which is medium or a material that responds with the change in temperature. Okay, so the keyword right here is they expand and contract in response to pressure. This is a bellows sensor, letter A. Number 214. It is a control device that monitors the temperature and changes in temperature for a particular process. Okay, again, it is a control device that monitors the temperature or changes in temperature for a particular process. This letter A, this is the bimetallic or thermocouple wires. The letter C, resistance temperature detectors. That's not it. Letter D, thermistors. These thermistors are resistors that, when heated or when the temperature is increased, they have changes also in the resistance. So the answer here is thermostat, letter B. Number 215. An electrical control device used to activate a switch for a defined temperature. Okay, so used to activate a switch for a defined temperature. So this must be a sensor. The answer is letter A. Number 216. The device used to control the amount of moisture present in storage room. So moisture present is this is related to humidity. So the answer right here is letter B, humidistat. Number 217. As an agricultural engineer, what electrical control devices would you recommend for poultry incubators? So for poultry incubators, what you need is the temperature and the humidity. So the answer here is letter B. Okay, number 200. Number 218. The 218. Rice mill equipment was imported in Japan using the JIS standards. If the red pilot bulb turns on on its control panel, what does the red light indicate? So we have three conditions right here. We have running. We can have an idle condition, and we have a fault condition. Okay, so if there's something wrong in the circuits, then that's fault, and idle is about to run, and running is the equipment is in good condition, or is in good running condition, or it's operating properly. Okay, so we have here different standards, and for JIS, the running condition is being indicated by the red light. So this is letter A. Number 219. For ANSI, the red is idle condition. And for 220, the equipment exported from Germany using DIN standards, a red pilot bulb indicates a fault. Okay, number 221. It is a type of switching device extremely useful when controlling a large amount of current and or voltage with a small electrical signal. The answer here is letter A. Number 222. It is a magnetically actuated device for repeatedly establishing or interrupting an electrical power input. Okay, this is a contactor. Number 223. It is a device in the manual motor starter to check for too much current and open the motor starter circuit before the motor windings become damaged. Okay, so recall in our graph right here, right, we have this inrush current and then we have this running current. And right here, there's a protection device that's called OL, or overload relays, and right here we have the circuit breakers. Okay, so for 223, it is a device in the manual motor starter to check for too much current and open the motor starter circuit before the motor windings become damaged. This is Okay, this is an overload relay. This is letter D. Okay, number 224. It is a motor switch. This is a combination of contactor and an overload relay. This is letter C, magnetic motor starter. Number 225. A grain blower is running at 1000 RPM. If the RPM is to be reduced to 700, which of the following is possible for reducing the speed? For letter A, it says install a variable frequency drive, and I have already mentioned this, that this VFD, or variable frequency drive, you can control the speed by adjusting the frequency. So this is for letter A, it can work. Also for letter B, install a gear motor. Actually, the reduction for a gear motor is quite high as compared to the belt drives. So because here in the gear motor you can have something like 1:10 or probably 1:15. So letter B, that depends upon the gear reduction. And for letter C, install a belt drive. Then actually you can do this. Okay, so I guess the answer here is let's just answer letter D. Number 226. A biomass-fed furnace is designed to use a blower to control the amount of air for the combustion of fuel in order to maintain the temperature required for the drying. As an agricultural engineer, what would you recommend to control the blower in providing the amount of air to the furnace? So the situation is that we have this, let's say we have these flatbed dryers, and right here is our blower. And of course, you need some heat source. And let's say this is our furnace. Right, so let's say this is our furnace. And it says here, biomass-fed furnace is designed to use blower to control the amount of air to maintain the temperature. Okay, so we need to maintain the temperature, so therefore what we need is a thermostat. And of course, you also need to have a motor controller. So we need to have a motor controller. The answer here is, for 226, this is letter C. For 227, it is a device used to vary the resistance. We have potentiometers, we have rheostats, and the difference between the two is one is for controlling the voltage, that's the potentiometer, and the other one, rheostat, is for controlling the current, and we also have the variac. So the answer here is letter D. Number 228, a timer in motor control is to: letter A, indicate the motor is overloaded. Letter B, increase the revolution of the motor. Letter C, delay or advance the operation of the motor. D, stop the motor. So the answer here is letter C. So it can delay or advance the operation of the motor. Number 229, which of the following is not correct? If the fuse element in an entire series circuit melts due to excessive current. For example, we have this circuit right here, and we have a fuse, right? We have a fuse. Okay, and it says here that it melts, so meaning that it was broken. So that means that, okay, let's say we have this voltage source, and we have this resistors, and we have this fuse. Then that means that letter A, the entire circuit is shorted. Letter B, the fuse element is opened. Letter C, the fuse protected the circuit components against overload. Letter D, the fuse is replaceable. Okay, so again, let us read again the number 229. Which of the following is not correct? Okay, so take note, it's not correct if the fuse element in an entire series circuit melts due to excessive current. For letter B, the fuse element is opened, so this is true. So B is true. Letter C, the fuse protected the circuit components against overload. Yes, this is true. Letter D, the fuse is replaceable. Yes, you can replace that. So the answer here is letter A. Number 230. So 230 is a part of a motor circuit where conductors are sized according to the current drawn by the motor. Okay, so this is, okay, if you recall that we have this, let's say we have this electric motor, then it's connected to an overload relay, and then connected to a contactor, and then connected to a circuit breaker, and then to the source. If you recall this diagram, okay, so here we connect some control circuits, and okay, and this one, okay, the term here, the circuits referring to this, this is the one they call power circuit. Okay, and the other one right here, that's what they call control circuit. So therefore, number 230, this is letter C, and for 231, okay, it's a part of motor circuit where it contains control devices. This is letter C. Number 232, it is defined as the brief closure of a motor circuit to energize a motor for a short period of time. Okay, so what this means is that, for example, I have this electric motor, okay, and I have this switch right here. Okay, so when I press this button, this will turn, this will rotate. The shaft of the electric motor will rotate. Okay, so when I press this button and I held it for a long time, then it will just continue to rotate. But if I don't press it anymore, then this one will stop. Okay, so that term is what we call jogging. This is letter A. And for the term plugging, this refers to a method of stopping a polyphase motor quickly by momentarily connecting the motor for the reverse rotation. So when I click this, instead of rotating clockwise, it rotates counterclockwise immediately. Okay, so if that's the case, that is what we call plugging. Letter B. Number 234, it is the simplest motor control circuit. This is across the line, letter C. And for 235, it's a motor control circuit where you can control the motor in two different stations. And this is a two-station motor control. Okay, letter B. And 236, it is a motor control circuit where the motor shaft can run clockwise or counterclockwise. And this is a forward-reverse motor control, letter D. 237 is a type of motor control circuit where the motor can be energized only by a short period of time. This is similar to number 232. This is letter A. Okay, now let's continue our review questions. Let's go to 238. I think we should have a brief discussion first regarding these electrical loads. And the concept about electrical loads is that it's simply about determining the currents and then sizing up the components. Okay, so just like in structures, if we have these loadings, example from the floor, okay, so that floor loading is being transferred to the beam, and then this beam is being transferred, the loads from the beams, it's being transferred to the columns, and then from the columns it's being transferred to the footings. Okay, so basically the idea is that for structural context, then we are sizing the elements or the structural members, okay, based on the loads, okay, and that loads we refer to as the structural loads. So right here we can see that we have a let's say a low or a smaller value of loads. Okay, this is right here, low loads, for example. But as you go to these components or structural members, you would see that this one carries much higher loads, right? Higher loads, simply because these ones, this footing, they're the ones carrying the loads of the columns, the beams, and then the floor live loads, and anything above this. Okay, so the same is also true in the context of electrical systems, because right here we have the loads from the, let's say, outlets, lighting outlets, and probably we also have loads from the convenience outlets, okay, and many more. So these loads, then it has to be transferred to these wires must be able to carry these loads, and then these wires must be protected from overloadings and other faults. So we have these breakers, for example, or overcurrent protection device, OCPDs, okay, and then it goes to the let's say to the meter, and then it goes to the service drop line or service drop wire, and to the distribution lines. Okay, so you would see here that right here we have low loads, right? We have low loads, and as you go, okay, so low loads for this wire, for this conductor, but right here you have higher, or let's say high loads. Let's say high loads. Okay, so basically it carries all the loads from this loads right here. Okay, or I'd rather say that we have a wire going to the convenience outlet, and then another wire going to the, or feeding the lighting outlets. Okay, so low loads as compared to the loads right here. So that's why we size this wire bigger, or the size of the wire is bigger here as compared to the wires in this side. Okay, so that's just the main idea here about electrical loads. And let's write here electrical loads, and that's these are in terms of the currents. Okay, and we have to size up the wires and electrical systems. We have to size up the wires, these circuit breakers, and many other devices. So just like here, we need to size the members based on the loads. Okay, so number 238. For 238 is the number of watts required by the electrical equipment in use in the building. This is letter A, electrical load. In number 200, this is 38. Number 239, refer to the table below. A proposed brooder house has a capacity of 15,000 baby chicks. Estimate the electrical load of this building. Okay, so this is just something like a rough estimate for the for this agricultural structure or agricultural buildings. And it says here, agricultural for poultry brooding, we have a minimum value of 5,150 watts. The design value is 4 watts per chick if small flock, and we have 3 watts per chick if large. And when you say large, this is 1,000 or more. and 4 watts per chick for any size flock with infrared brooders. Okay, so from the table, from the table, you can actually select that the 3 watts per chick, okay, times our 1,500 baby chicks, which is just equal to 4.5 kilowatts. And for number 240, if an infrared brooder is used, okay, so if an infrared brooder is used, then we have to use this 4 watts per chick, right, times our number of baby chicks. This is equal to 6 kilowatts. Okay, so the answer for 239 is letter C, and 240, this is letter A. Next item, 241, determine the monthly energy consumption of a farmhouse having the following appliances. So we have 1,200, or let's just write in terms of kilowatts. Okay, so this is 1.2 kilowatts of electric iron at 2 hours. Right, so this is 2 hours, and recall that when we talk about electrical energy consumption, our unit would be in kilowatt hour. Okay, so 1.2 kilowatts, that's for 2 hours. And then 1,000 watts or 1 kilowatt for water heater at 3 hours. And another one, 1.3 kilowatts for toasters at 30 minutes. So this is 0.5 hours. And what else? If the average cost of energy is 10 pesos per kilowatt hour, what is the total cost of energy used in 30-day consumption? Okay, so first let's multiply this. 1.2 times 2, we get 2.4 kilowatts hour. And right here, 1 times 3, this is 3, and this one is 0.65. And our energy consumption is, okay, this is 6.05 kilowatts hour. Okay, so now let's multiply this. 6.05 kilowatt hour, okay, times this is actually kilowatt hour per day, okay, times our 30 days per month. Okay, 30 days per month, right, times 10 pesos per kilowatt hour. Okay, per kilowatt hour. Okay, so if we do the math, what we get is a value of 1,815 pesos. So the answer here for 241 is letter C. Okay, now let's go back to our lecture discussions or lecture presentations before we continue our review questions. Okay, this is our sixth topic for the review course in agricultural electrification and controls. For the title of this topic, this is electric distribution systems. For the contents, we'll first discuss an overview of the electric distribution, and then we'll get into the details of the service entrance, and then the overcurrent protection devices, and finally the branch circuits. So for the electric distribution, basically it answers the question of how do we get, or how do we have the power source from let's say from the residential or commercial buildings. So that is being transmitted from the power generating plants, such as the coal power plant or hydroelectric power plant, or any generating plants that produces power. That is electrical power. So in this power generating plants, it is being produced at this some high value of voltage. So this is 12 kV, so that's around 12,000 volts. But right here we only have 240 volts. Okay, so how did that happen? Okay, so it has to have some step-up transformer, and recall that a transformer is an electrical device that either increases the voltage or decreases the voltage, and of course in return there's going to be an effect in the electrical currents. Right here there's a step-up transformer. Okay, so you would notice that these generating plants, they are miles away from the load. Okay, so now let's refer this as the load, whether that's residential or commercial or any other terms. Okay, so that's miles away. So because of the distances, then there's actually losses along the lines, and that's why it has to have this higher values. Okay, so right here it's being stepped up, and then it's being transmitted across or along these transmission lines. So those high towers or truss type towers that we see along the highways, that's the transmission lines. Okay, and that carries, let's say we have this, for example, 400 kilovolts, and then it's being transmitted to some substation so that the voltage will lower down. So after this substation, it's then being transmitted to the distribution lines. Okay, so that is just a something like a post, which is lower as compared to these transmission lines, and the voltages that it carries is around 13 kV or less. So but right here we have 400 kV. Okay, and then we have transformers right here. There's another transformers, the ones you see, and the distribution post where it has this let's say this drum, something like a drum component. Okay, and that's the transformer. Okay, so because of that transformer, then the voltage can be dropped to 240 volts. Okay, so here is our transmission lines, and these transmission lines run between substations, and they are higher and carry high voltages. Right here, this is our figure 4 substation that transforms voltage from high to low or low to high. And we have here the distribution lines. So these distribution lines run from the substation to the end user locations, and this is it. This post right here, that's the one I was talking about, and these electrical devices, they are called, they are the transformers in this power lines. And then here in our distribution post, it looks like this, and it has also some components right here, like for example 3 fuses, and we have transformers if it's 3-phase, or it can be single phase. Okay, now let's talk about from this transformer, how does it get into the end user. So there's a wire, actually there's a wire. Okay, so from this transformer there's a wire, and that wire is what we call the service drop wire. Okay, so the service drop wire enters this this material called weatherhead or entrance cap. Okay, and that wire enters this conduit, and this conduit is termed as the mast. So that's why sometimes it's called as the mast head and then it goes to the meter. So we have a metering device right here, and then sometimes there's also some switches or protections right here in this service disconnect. Okay, so from this point, that's the service entrance. Is that portion that runs from the utility lines to the point of attachment at the weatherhead. Then, okay, so this is it. Then down to the entrance cable or conduit to the meter. Okay, so that's actually I'm not sure if it's here or right here. Okay, so that's the service entrance, and it is where the electric utilities maintenance responsibility and the building owners begins. Okay, so from this, let's say this is our meter, this is our mast or conduit, and this is our mast head. Okay, so from this point that's where the electric utility maintenance responsibility ends, and in this load side, that's where the building owners or the end users responsibility begins. Okay, and we have here a minimum clearance requirement, so that refers to this one. Okay, so what's the minimum requirement? So you would notice that sometimes this is installed above the roof, right, or sometimes outside or along this concrete post. So what's going to be the head, the clearance? So we have here a minimum clearance requirement, so it can be above the roof, and there's something, some values here, probably 2 to 3 feet. And we have also a vertical clearance from the ground if less than 600 volts. Then it says that we have a 3,000 or 3 meters, and we also have 3.6 meters if it's a residential and commercial, not subject to traffic. So if the load is 300 volts. But if it's greater than 300 volts, then it's 4.5 meters. And if it's along the public streets, alleys, and highways, then that should be 5.5 meters. And we also have other criteria here, like for example, from the building opening or the swimming pool. And this one's, what's included is these values only. Okay, next is, we are done with this, right? This is our service drop wire, and this is our masthead, this is our conduit, this is our meter. And from this meter, or some switches right here, there's a line that goes to our final overcurrent protection devices. Okay, so this term right here, that's the final, that's where the circuit breakers, right? Circuit breakers are. Okay, and if we talk about the final circuit breakers, because it's also possible to have another panels right here for let's say electric motor loads and things like that. But if you're referring to the final overcurrent protection device, okay, from this device to this one, this what we call, if I'm not mistaken, this is referred to as feeders, or main feeders, or sub feeders if there are subs. Or right here, that could also be a sub feeder, right, to another overcurrent protection device. Okay, so this one, it looks something like this. So we have here a lot of circuit breakers right here, and we have a main breaker. So this circuit breaker is probably, let's say here is attached or is connected to one branch circuit for lightings, for example, and here another branch circuit for convenience outlet, or another branch circuit for another convenience outlet, or things like that. Okay, so these are protection devices, and in description, they protect the circuits and equipment from, okay, number one, from overload, and then number 2 from short circuit, and from number 3 from ground fault. And when we see overload, that's a condition wherein the conductors or the wires carry excess current. And for short circuit, this is an unintentional electrical connection between two conductors. Okay, so moving on, these OCPD devices can be circuit breakers or fuse. And when we say fuse is an OCP, overcurrent protection device, that opens when there is an overcurrent in the circuit. Okay, so in symbol we draw this, and for example, the current that runs through this conductor is too much, then this one will just break. Okay, so that's the fuse. But for circuit breakers, it is an OCPD equipped with automatic tripping device to protect the branch circuit. So, and the most common type is the thermal magnetic type, so something like this. So when you say trip, this switch right here, it goes down, right? It trips. If it senses if it senses an overcurrent, then it trips. Okay, so you would also notice right here there's a value like 20 and 30. So this corresponds to the overcurrent rating, and that refers to the highest amperage it can carry continuously without exceeding a specific temperature limit. So for example, the branch circuit is lighting for lighting outlets, for lighting outlets. Then there's a specified for typical applications like maybe 15 amperes, and for convenience probably 20 amperes, although there are just some rule of thumbs, but you also have to check it in the calculations as well. Okay, and finally, we're done with this, and as I have said, it is also possible to have another let's say another OCPD, right? It's also possible, and if that's the case, then this one will be the sub feeders, and this one will be the main feeder. Okay, so probably a typical application is that if you have this main panel boards, then we can have also we can separate the power circuits, right? Let's say these are our power circuits, and this will be our lighting circuits. So here there's a lot of branch circuits. Okay, so something like that. Now, what is this branch circuit? This branch circuit is, or refers to, the circuit conductors between the final overcurrent protecting device and the outlets. So here are our outlets. This symbol is a lighting outlet. Okay, so from this outlet to this, then this wire right here, this is our branch circuit. Okay, so the same is also true for our convenience outlet. Okay, so for our convenience outlets, the wire that runs from the convenience outlet to the final over current device, so this is another branch circuit. Okay, and for the types of branch circuits, we have general purpose, we have also appliance branch circuit, and we also have individual branch circuit. Now for a general purpose, we have this description. They're branch circuits for supplying lighting fixtures and receptacle outlet for most small portable appliances. But if you have a bigger appliance, let's say a refrigerator or air conditioner, then that branch circuit, let's say, supplies one or more outlet to which the appliances are to be connected. And the difference with this, that this one refers to portable appliances. Again, for individual, for one utilization equipment, for example, pump. Okay, so because pump electric motors connected to this, pumps or heaters, they require individual branch circuit. Okay, and additional note right here, branch circuit conductors supplying a single motor shall have an ampacity of not less than 125% of the motor full load amperes. Alright, now we'll go on to our review questions.